Hello and welcome to this video on standardizing data in a normal distribution. So far we have talked about the empirical rule, also known as the 68-95-99.7 rule. This rule tells us that about 68% of the data is within one standard deviation of the mean, about 95% of the data is within two standard deviations of the mean, and about 99.7% of the data is within three standard deviations of the mean. Now, this is really useful if we want to know information about data points that are on the standard deviations. So, for example, in 1973, a study was done by the CDC. This found that 12-year-old boys had a mean height of 151.1 centimeters with a standard deviation of 8.18 centimeters. So if we look at our normal curve, here's our mean, 151.1, and here are all of the data values that lie on multiples of our standard deviation. If we want to know the percent of boys between 142.92 and 159.28, we are looking at the percent of boys that lie in this area. Here, one standard deviation back, to here, one standard deviation forward. So we want to know this percent, and we can do that with our empirical rule because between one standard deviation back and one standard deviation forward, we have 68% of all of the data. So this question is pretty easy to answer with our empirical rule. It gives us 68%. The problem with this rule is that it only covers data that is on our standard deviations. So what happens when the values that we're dealing with are not multiples of standard deviations? All right, so here's the same study we had before, same curve. This wants to know what percent of boys in 1973 were less than 145 centimeters in height. If I want to know less than 145 is somewhere around here. And so I want to know all of this area. So the idea is I want to find the area under the curve. It turns out that this is actually a little bit tricky for us to do. It gets into some pretty intense calculus, which we won't deal with in this class. To find the area under the curve, it turns out there's a fairly simple algebraic transformation that we can apply, which would change any bell curve with any values here into a standard normal bell curve. When we have a standard normal bell curve, it looks like this, where the mean is now 0. So this is now our mean mu, and our standard deviation is equal to 1. Standard normal curve, mu is equal to 0, and standard deviation is equal to 1. The transformation that we use to go from a normal curve like this one, where mu is the actual data mean and standard deviation is the actual standard deviation given, to the standard normal curve, where mu, the mean, is now 0 and the standard deviation is 1, is given by this equation. Z equals x minus mu over sigma. X is the data value that we were playing with. Mu is the mean of the data, and sigma is the standard deviation of the data. Z is what we call the z-score, and this is the value on the standard normal curve that the original data value corresponds to. So I have this question: what percent of boys in 1973 were less than 145 centimeters tall? I know that 145 is sitting here. The first thing I want to do to answer this question is figure out, on the standard normal curve, what does 145 centimeters correspond to? I've got x equals 145. This is the first one we're going to practice with. Then we can practice with x equals 160. And I want to figure out where this value, which is about here on the normal curve with the actual data values, corresponds to what on the standard normal curve. Just by looking at this, since 145 would be about here on the normal curve, we can see that that's between the mean and 1 standard deviation back. So we can expect on the standard normal curve, 145 will also be about here, which means the z-value looks like it'll be somewhere between 0 and -1, closer to -1. To actually calculate the z-value, which remember is the position on the standard normal curve that the data value 145 corresponds with, we use this formula. So z equals 145 minus 151.1 all over 8.18. Put this into your calculator and you get -0.75. Now I am rounding this to 2 decimal places because most standard normal tables round to 2 decimal places. We will take a look at the table in the next video. What we have found is that the data value of 145, which occurs in the original normal distribution, corresponds to a z-score of -0.75 on the standard normal curve, which is about what we expected. If a 12-year-old were 145 centimeters, that would be 0.75 standard deviations below the mean. Now let's practice this one more time with the next data value. And then in the next video, I'll show you how to use this information to find the percent of data that is below this or above this. For our second example, we want to standardize the data point of 160 centimeters. This would be a 12-year-old who is 160 centimeters or above. We can see that 160 centimeters is right here, just above 1 standard deviation above the mean, which means on the standard normal curve, we would expect it to be just above 1 standard deviation above the mean. And so our z-score will be just above 1. Again, to calculate this, we're going to use this formula. Our z-score is 160 minus 151.1 divided by 8.18, and we find that to be 1.09. Again, I rounded to 2 decimal places because that's what most standard normal tables do. The main reason we're doing this is that the area under the curve for all these normal distributions is quite hard to find. But if I transform it to a standard normal distribution, this is so common that people have actually found all of the areas for us and made tables or simulations for us to use. So we don't have to go through all of that calculus to get the areas ourselves. You will see standard tables in the next video.